Reversible process is that which can be reversed in such a way that all changes occurred in direct process. Next one, what it is a reversible process is that which can be retraced back in the opposite direction also is called as reversible process. Reversible process is that which can be reversed in such a way that all the changes occurred in direct process. Example, all isothermal and adiabatic changes performed slowly. All isothermal and adiabatic changes performed slowly is the example for reversible. And similarly, slow expansion and compression is the example for reversible process. Next one, irreversible process. A process which is not reversible exactly. A process which is not reversible exactly is called the irreversible process. Okay. Next one, irreversible process means a process which is not reversible exactly is called the irreversible process. A process in which the reversal does not take place is called as an irreversible process. Examples, the conduction of heat from hot body to a cold body. The conduction of heat from hot body to cold body. And second one, work done against friction. And all natural processes are the example for irreversible process. Are you got it? Definitions? Which is retraced back in opposite direction is reversible. Which is not retraced back in opposite direction, not reversible exactly is called irreversible process. Next, second law of thermodynamics. Second law of thermodynamics, we have two definitions. One is Clausius statement, one is Kelvin statement. The second law of thermodynamics can be stated in the following two ways. The second law of thermodynamics can be stated in the following two ways. First one, Clausius statement. Second one, Kelvin statement. What is Clausius given one type of statement and Kelvin also giving step. Both are same meanings only, but somewhat different is there in according to Clausius and Kelvin. It is impossible for a self-acting machine. It is impossible for a self-acting machine working in a cyclic process unaided by an external agency to transfer heat from a body at lower temperature to a body at a higher temperature. It is impossible for a self-acting machine. It is impossible for a self-acting machine working in a cyclic process unaided by an external agency to transfer heat from a body at lower temperature to a body at higher temperature. Hence, what it is, without any external agency, the heat does not transfer from lower body to lower temperature to a body at higher temperature. Always temperature is transferred from high region to low region. So without any external agency, the heat does not transfer from low temperature to high temperature. Hence, heat cannot flow from a cold body to a hot body without the performance of work by some external agency. Next one, Kelvin statement. It is impossible to derive continuous supply of work. It is impossible to derive continuous supply of work by cooling a body. It is impossible to derive continuous supply of work by cooling a body to a temperature lower than that of the coldest of its surroundings. Means one body is a certain temperature is there. If you want to reduce the temperature, it is not less than that of the surrounding temperature. That is the Kelvin statement. The first law of thermodynamics gives an equivalence between heat and work. It gives the relation between heat and work. First law does not give any limitations or conditions. First law does not give any limitations or conditions for this conversion, that is how much heat is converted into work and whether the transformation takes place high level to lower level or low level to high level, high level to low level or low level to high level. The answer of those concepts is nothing but Kelvin statement. Next, we want to derive the Kelvin scale of temperature. Kelvin scale of temperature and thermodynamic scale of temperature. It is essay question. Next important topic is Kelvin scale of temperature or thermodynamic scale of temperature. Kelvin scale of temperature or thermodynamic scale of temperature. Is it visible on the screen? Students, is it visible, ma? Is it visible, Nana?
Yes, ma'am.
Okay. Kelvin scale of temperature or thermodynamic scale of temperature. Important, ma, this topic. What is Kelvin scale of temperature? The ratio of heats is equal to ratio of temperatures. The Kelvin scale of temperature or thermodynamic scale of temperature is that scale. The ratio of the Kelvin scale of temperature or the thermodynamic scale of temperature is that scale. The ratio of any two temperatures, the ratio of any two temperatures is the same as the ratio of the heats observed. The ratio of any two temperatures is the same as the ratio of the heats absorbed and rejected by reversible Carnot engine and rejected by reversible Carnot engine. Operate between these two temperatures. Operate between these two temperatures, which is Q1 by Q2 is equal to T1 by T2. The Kelvin scale of temperature or the thermodynamic scale of temperature is that scale. The ratio of any two temperatures is the same as the ratio of the heats absorbed and rejected by the reversible Carnot engine. Operate between the two temperatures. Therefore, Q1 by Q2 is equal to T1 by T2. So how to prove this ratio means we are taking proof. For that, according to Kelvin, the efficiency of the efficiency of heat engine working between two temperatures. Working between two temperatures means here highest temperature is T1, here down temperature is T2. In between one, that is nothing but working substance A, B. According to Kelvin, the efficiency of a reversible heat engine working between two temperatures is a function of two temperatures only and is independent of the nature of working substance. Therefore, here highest temperature is T1, source is Q1. Here heat is Q1 minus Q2, and second situation is Q2. WB is equal to Q2 minus Q3. W1 is equal to Q1 minus Q2. WB is equal to Q2 minus Q3. Here Q1, Q2, Q3. Then consider now what it is, ma. Consider a reversible heat engine A absorbing Q1 amount of heat energy at temperature T1. So it traces, no, my arrow mark shows the amount of heat is taking from source T1 and giving rejected to Q2 amount of heat to the sink temperature T2. According to the Kelvin statement, neta is equal to 1 minus Q2 by Q1. That is equal to function of temperatures T1 and T2. Therefore, 1 minus Q2 by Q1 is equal to F of T1, T2. Therefore, Q2 by Q1 is equal to that F of T1, T2, take this side. Then it becomes Q2 by Q1 is equal to 1 minus F of T1, T2. Both sides we are taken as one subtraction. Then what it is, this minus take that side, that F of T1, T2 take this side. Then it is 1 minus F of T1, T2 that equal to Q2 by Q1. Reverse means Q1 by Q2 means 1 by it becomes. This equation is reverse. Then Q1 by Q, here Q2 by Q1. Now we are taken as Q1 by Q2 means it becomes 1 by F1 by 1 minus F of T1, T2. Therefore, Q1 by Q2 is equal to, it is in the function of F of T1, T2, which is equation number 1. You followed my, is there any doubt? Efficiency of heat engine neta is equal to 1 minus Q2 by Q1. We are taken as function of temperatures T1, T2. 1 minus Q2 by Q1 is equal to F of T1, T2. Then Q2 by Q1 is equal to 1 minus F of T1, T2. Then Q1 by Q2 is equal to 1 by 1 minus F of T1, T2. Then reverse of that means Q1 by Q2 is equal to function of capital F you are considering. That is equation number 1. Function of temperatures T1, T2, which is equation number 1. Is it clear? Okay, after that, now we consider another reversible heat engine B absorbing heat Q2, absorbing up to that one engine, after that another heat engine from that B to temperature T3. Therefore, now we can take screenshot ma and copy the notes. Okay, then it is easy. Are you following? Now we consider another reversible heat engine B absorbing heat Q2 at temperature T2 and rejecting heat Q3 at temperature T3. Then Q2 by Q3 is equal to another function f of T2 comma T3, which is equation number 2. Now what it is, similarly we can take the another reversible engine. Similarly we can take the another reversible engine which is working between T1 and T3. Then Q1 by Q3 is equal to f of T1 comma T3. Q1 by Q3 is equal to f of T1 comma T3, which is equation number 3. On multiplying equations 1 and 2, on multiplying equations 1 and 2, on multiplying equations 1 and 2, then what it is my LHS multiplying and RHS multiplying. Q1 by Q2 into Q2 by Q3. Q2 gets cancelled. Then Q1 by Q3 is equal to f of T1 comma T2 into f of T2 comma T3. F of T1 comma T2 into f of T2 comma T3. Then what it is from equation 3 and 4, what we are writing? Q1 by Q3 is equal to function of T1 comma T3 that we are multiplying, we are getting from equation 1 and 2. Then finally what it is, Q1 by Q3 is equal to f of T1 comma T2 into f of T2 comma T3, which is equation number 4. Therefore, from equations 3 and 4, f of T1 comma T3 is equal to f of T1 comma T2 into f of T2 comma T3, which is equation number 5. Are you following? F of T1 comma T3 is equal to f of T1 comma T2 into f of T2 comma T3. F is nothing but here function. Now we are considering one more function with respect to f of T1 comma T2 is equal to phi of T1 by phi of T2. Another function phi we are considering and f of T2 comma T3 is equal to pi of T2 by pi of T3, which is equation number 7. Now, where phi is the another function of temperature, Therefore, f of T1 comma T2 into f of T2 comma T3 is equal to pi of T1 by phi of T2 into pi of T2 by phi of T3. Pi of T2 gets cancelled. Then pi of T1 by pi of T3. Therefore, function of T1 comma T2 into function of T2 comma T3 is equal to function of T1 comma T3. So from equation 1 and 6, finally what we are concluding f of T1 T2 means phi of T1 by phi of T2. Similarly, f of T2 comma T3 means phi of T2 by phi of T3. Then finally what we wrote Q1 by Q2 is equal to phi of T1 by phi of T2, that equal to T1 by T2, which is equation number 8, which is only Kelvin scale of temperature. Starting also we taken that definition only, no? Is it audible, ma, again?
Yes, ma'am.
Problem. Okay, okay. Is there any doubt in Kelvin scale of temperature? Next, entropy, ma. Next topic is entropy. What is entropy means? The thermal property.
Ma'am, ఒకసారి previous slide చూపియరా?
Which one, ma? Kelvin scale of temperature?
Yes, ma'am.
Slide, screenshot?
లేదు మ్యామ్, ఒకసారి చూపియండి, తీసుకుంటాం.
Wait. First one.
Completed, ma'am.
Okay. Next we start screen share. Intro visible, Nana? Students, is it visible on the screen?
No, ma'am.
Entropy. Thermal property of a body remains constant along heat during an adiabatic process is known as entropy. Next, take the definition of entropy. What is entropy? Thermal property of body which remains constant. The thermal property of a body which remains constant is the thermal property of a body remains constant.
Is it visible, ma? Technical issue continuously.
No, ma'am.
Now also not visible, ah?
Visible, ma'am.
The thermal temperature we are asking 1 by T1 by now. Just now Q1 by 2. Q1 by is equal to T is two different that T2 T3. Here Q1 by T1 is equal to Q2 by T2. T situation number 1. Similarly, cycle cycle is A, B, C, D. First diagram. So first is C, D, A, and second block is C, D, A. Number. Similarly, we consider a reversible cycle ZDESC. From this, we are taken Q2 by Q2 by Q3 is equal to T2 by T3. Then Q2 by T2 is equal to Q3 by T3, which is equal to 2. Now from equations 1 and 2, from equations 1 and Q1 is equal to Q2 T2 is equal to Q3 by T. First equation Q1 is equal to Q1 is equal to first equation is Q3. So finally, what we are writing Q1 by T1 is equal to Q by T2 is equal to Q3 by T. Finally, what Q simply Q by T
function of internal state of a body. To Q by T, that equal to constant S. Therefore, entropy S is called entropy. Entropy is a definite function of internal state of a body. We can't measure the absolute temperature of a substance, but we can measure the change in entropy. We can't measure the absolute entropy of a substance. We can't measure the absolute entropy of a substance. We can measure the change in entropy. Next, physical significance of entropy. Physical significance of entropy means the ratio of an amount of heat added or subtracted. The ratio of an amount of heat added or subtracted to the temperature is called the change in entropy. The ratio of an amount of heat added. The ratio of an amount of heat added or subtracted. The ratio of an amount of heat added or subtracted to the temperature is called the change in entropy. Therefore, change of entropy is equal to heat. Change of entropy is equal to heat energy by temperature. Therefore, ds is equal to dq by t. On integrating above equations, integral s1 to s2 ds is equal to integral dq by t. Therefore, what we are taking, integral s1 to s2 ds is equal to integral of dq by dt. Integral of dq by dt. Is it visible on our screen? Entropy disorder. So integral s1 to s2 ds is equal to integral of dq by t. Integral of dq by t means temperature only. The ratio of heat to temperature in an adiabatic process is called entropy. The thermal property of a body. The thermal property of a body which remains constant along heat. Which remains constant along heat during an adiabatic process. Which remains constant during an adiabatic process is known as entropy. Therefore, S2 minus S1 is equal to integral dq by t. The entropy is a real physical quantity. The entropy is a real physical quantity and is a function of the state of a body. The entropy is a real physical quantity and is a function of the state of a body. Entropy may play the role in heat motion. Entropy may play the role in heat motion similar to the mass play the linear motion. Hence, entropy may be treated as thermal inertia. Entropy may play the role in heat motion similar to the mass play the linear motion. Hence, entropy may be treated as thermal inertia. Increase of entropy of a system implies transition of thermal energy from more available to less available form for conversion into work. Therefore, entropy is a measure of disorder of measure of disorder of molecules. Entropy is a measure of disorder of molecules of a system. Next, entropy disorder. The entropy of a system is a measure of the disorder quantity. That is the disorder quantity. So what is entropy, order and disorder? 4 marks question important. What is entropy? What is the physical significance of entropy? And what entropy, how it is changing in different reversible and irreversible process, including all change in entropy in reversible process, change of entropy in irreversible process, change of entropy for a perfect gas, and change of entropy for pressure and temperature, different equations we have. So that here we can take the entropy. Entropy is a real physical quantity and is a function of the state of a body. Entropy may play the role in heat motion, similar to the mass play the linear motion. Next, entropy disorder. Entropy disorder means the entropy of a system is a measure of the disorder quantity. That is, the disorder quantity increase, the entropy also increases. For example, a solid substance consists of atoms, and a solid substance consists of atoms and molecules arranged in a systematic way, and molecules arranged in a systematic way. That is the disorder quantity is approximately, that is the disorder quantity is approximately 0. The liquid state is less disorder state. The liquid state is less disorder state. In gaseous state, we can't specify the arrangement of molecules due to their random motion. Therefore, a substance is converted from solid state to liquid state. A substance is converted from solid state to gaseous state. The disorder increases, so that the entropy is also increases. According to Boltzmann's probability, according to Boltzmann's probability theory, the relation between, according to Boltzmann's probability theory, the relation between entropy and disorder, S is equal to K log EW, where S is equal to entropy, K is equal to Boltzmann constant, W is equal to disorder quantity. The entropy of a system is a the entropy of a system is a measure of the degree of disorder prevailing among its molecules. Example, free expansion, heat conduction. Example, free expansion and heat conduction. Okay, ma? Entropy disorder. Entropy and available energy. Entropy universe. Principle of degradation. The available energy of the universe is tending towards 0 is called as degradation. The available energy of the universe is tending towards 0 is called principle of degradation. The entropy of a system remains constant in reversible process, but increase in all irreversible processes. Thus, there is a change in entropy of the universe due to the reversible process. While the entropy of the universe increases due to the irreversible process, as all actual processes are inherently irreversible. Hence the entropy of universe increases. Whenever an irreversible process takes place, a certain quantity of energy of the universe is converted from a form in which it was available for work into a form in which it is unavailable for work. Now, what it is you want to calculating here, entropy in different process. One is change of entropy in reversible and irreversible process, and principle of degradation, entropy and available energy. Now we are considering entropy and available energy. For that, I will send you screenshot. Now is it visible, my screen? Students. Now is it visible, ma? Consider reversible engine work between temperatures T1 and T2 so that the efficiency of the reversible engine is exist up to T1 and T2. Let Q1 is the amount of heat observed. Let Q1 is the amount of heat is absorbed at high temperature T1 and Q2 is the amount of heat is released. Q2 is the amount of heat is released at lower temperature T2. Then work done is equal to available energy. Work done is equal to available energy that equal to Q1 minus Q2 that equal to Q1 into 1 minus Q2 by Q1, which is equation number 1. But we know that according to thermodynamic scale of temperature, but we know that according to thermodynamic scale of temperature, Q2 by Q1 is equal to T2 by T1. From equation 1, what we are taking, ma? Available energy Q1 of 1 minus T2 by T1, which is equation number 2. Now, let quantity Q is conducted from the body of higher temperature to lower temperature. Let T0 is the coldest temperature. T0 is the coldest temperature with respect to surroundings in the universe. T0 is the coldest temperature with respect to the surrounding in the universe. So that T0 less than T2 less than T1. By using equation 1, available energy before transfer is equal to Q into 1 minus T0 by T1. Available energy after transfer is Q into 1 minus T0 by T2, which is equation number 4. Therefore, loss of available energy. Loss of available energy, how much, ma? Equation 4 minus equation 3. That we are taking 3 minus 4 means Q into 1 minus T0 by T1 minus Q into 1 minus T0 by T2. In both the terms, now we are taken as common Q. Therefore, T0 by T2 minus T0 by T1. In both the terms, again, T0 is common. Then what we have, ma? Q by T2 minus, take Q inside. T0 is before. Then T0 into Q by T2 minus Q by T1. Now T0 is common means Q by T2 means S2. Q by T1 means S1. Therefore, T0 into S2 minus S1, which is equation 5. Therefore, loss of available energy is equal to T0 into ds. Therefore, from equation 5, by increasing the change in entropy, unavailable energy is increases. From equation 5, what we are taking, ma? By increasing the change in entropy, unavailable energy is increases. So that there is an unavailable energy of the universe. So that there is an unavailable energy of the universe is continuously decreasing. Is it clear? Next, change in entropy in reversible process. My next short answer question is change in entropy in reversible process we have. Now is it visible on the screen, ma? Students.
Yes, ma'am.
Now.
Ma'am.
This is important. Take screenshot and write down in the notes, ma. Maintain separate notes for this physics third sem. Okay. Okay, ma.
Yes, ma'am.
Okay. Take the screenshot, ma. Now, change in entropy of reversible process means here we can take the two temperatures. Consider two adiabatic process A, B and two isothermals at T1 and T2 as shown in figure. Now, what we are taken here? What we are taking, consider two adiabatics A and B and two isothermals at T1 and T2 as shown in figure. T1 and T2 and temperatures A1 and A2 as shown in figures, no?
Yes, ma'am.
So here the process is what, ma?
Releasing.
So what is the entropy? Entropy is a temperature T1, T2, absorbing heats are Q1, Q2. Then what we are considering here, ma? Two temperatures. First isothermal process expansion AB, increase in entropy is Q1 by T1. And similarly, during adiabatic expansion BC, there is no change in entropy. Then what it is, ma? During isothermal compression and during adiabatic compression, we are taken as entropy. During isothermal expansion, AB increase in entropy is equal to Q1 by T1. During adiabatic expansion BC, there is no change in entropy. Therefore, during isothermal compression CD, decrease in entropy is Q2 by T2. Then we are taken circle, ma. Matter is the understanding bull. Then during the adiabatic compression DA, there is no change in entropy. The change in entropy during reversible cycle is Q1 by T1 minus Q2 by TT. But we know that according to thermodynamic scale of temperature, simply Q1 by T1 is equal to Q2 by T2, which is equation number 2. Now we are substituting this value in that value. Then what it is, ma? Substitute equation 2 in equation 1. Then delta S is equal to Q2 by T2 minus Q2 by T2, ma, that equal to 0. Therefore, there is no change in entropy. Therefore, there is no change in entropy in the case of reversible process. There is no change in entropy in the case of reversible process. So that entropy remains constant. So that entropy remains constant in the case of reversible process. Important, ma. Entropy remains constant in the case of entropy remains constant. Okay. So once you identify that derivation part, ma, is there any doubt? Ask. I'm waiting here. More 3-4 minutes is there, no? Okay, Nana?
Yes, ma'am.
Consider an irreversible engine. So is there any doubt, ma?
No, ma'am.
Huh? Is there any doubt in derivation part, Nana?
No, ma'am.
Okay, that is important for 4 marks, ma. Next, change of entropy in reversible process, change of entropy in irreversible process, both are important. Consider an irreversible engine is working between the amount of heats Q1 and Q2, so that the efficiency of the irreversible engine is given by neta1 is equal to 1 minus Q2 by Q1. Now consider the reversible engine is working between the two temperatures T1 and T2. So that what it is, ma? We can take as one more steps here. Now I want to share that. Wait. Next, the efficiency of the reversible engine. The efficiency of the reversible engine is given by neta R is equal to 1 minus the efficiency of the reversible engine is given by neta is equal to 1 minus T2 by T1. Ma. Therefore, for an irreversible process, the efficiency is less than that of the reversible cycle. So that the efficiency of the reversible cycle operating between the two same limits. The efficiency of the reversible engine is operating between two same temperature limits. Hence, 1 minus Q2 by Q1 less than, hence 1 minus Q2 by Q1 less than 1 minus T2 by T1. Q2 by Q1 greater than Q2 by Q1 greater than T2 by T1. Therefore, Q2 by T2 greater than Q1 by T1. Finally, what we wrote, ma? Q2 by T2 minus Q1 by T1 greater than 0. Q2 by T2 minus Q1 by T1 greater than 0, which is positive. Which is positive. Hence, the entropy of the system. Hence, the entropy of the system remains. Entropy of the system remains increases maximum value in the irreversible process. Entropy of the system is 0 minimum in a reversible process, and entropy of system increases in all irreversible process. Is it clear? Okay, Nana?
Yes, ma'am.
Now next class will continue, ma. That is entropy not required, entropy temperature indicator diagram and Carnot cycle we will discuss in next class. Okay, problems and depending upon Carnot cycle and thermodynamic potentials, that are all are important in the continuation part. Here today class we completed entropy.
Yes, ma'am.
Is there any doubt? Once you go through your textbooks also, ma, you have any difficulties identified, you can ask in further classes.
Okay, ma'am.
Okay. Shall I leave the meeting?
Ma'am,
Yes, ma'am.
చేంజ్ ఇన్ ఎంట్రోపీ రివర్సిబుల్ ముందు కొన్ని స్లైడ్స్ పెట్టారు కదా, ఒకసారి సెండ్ చేయరా అవి?
Change in reversible before, that is what my temperature diagram, entropy, Kelvin scale of temperature, that is sended.
ఎస్ మ్యామ్, ఒకసారి పిక్చర్స్ చూపియరా, స్క్రీన్ షాట్ తీసుకుంటాం.
This is first Kelvin scale of temperature, ma. Is it visible, Nana?
ఎస్ మ్యామ్.
Next. One more screen is there for related to Kelvin scale of temperature. This one. Okay, Nana, up to this Kelvin scale of temperature, write these notes.
ఓకే మ్యామ్, థ్యాంక్ యూ మ్యామ్.
Okay, Nana.